So the first one's pretty simple. It's just two atoms bonded together, all right? And they're both hydrogens, all right? So our example is going to be H2. And there's not a good place to kind of draw this on here, so I'm just going to kind of draw it around here. The reason that these two go together is because of how many valence electrons hydrogen has. So hydrogen has how many valence electrons? Just one, right? So that would be like an H with one dot. And then if you had another H, it would have its own dot, right? And for hydrogen, how many valence electrons does it want to have? It only wants to have two, right? That'll fill it up. So if hydrogen shares with another hydrogen, now they both have two because they're sharing, right? So that's kind of why this works for hydrogen, all right? Hydrogen's one of kind of the exceptions because most of the time they want to have 8, but hydrogen's one of the few that only wants 2 because it's the first energy level. We're going to see a few more exceptions and then we'll get into the 8 ones. Okay, but what about the shape? So the shape is not very complex, so we're just going to call it linear. Linear, it's like a little line. Right? And that's pretty much all we can say about that one because there's no central atom for it. And a big thing with all of these is there's a central atom for all of them. All right, so let's look at the next one. The next one looks like this here, and I 3D printed the middle part because we didn't have one that really worked well with this. This is going to be beryllium, and then we're going to bond 2 hydrogens to it, and it's going to form this kind of shape right here. So our example is BeH2. It's also linear, right? But we need to distinguish it from this top one, so we're going to call it triatomic linear. So it's triatomic linear, all right? And for the rest of this, we're going to do something over here first. Now, this has a central atom, right? For whatever reason, to have a central atom, they're going to call that an A, all right? And then any atoms that are attached directly to that A, that central atom, they're going to be X. And that makes more sense because they're talking about like external atoms here. So we have an A in the middle, and then we have 2 X's. So what we're going to call this is AX2, all right? And that means you have 1 atom in the center and then 2 atoms connected to it, and that's it, all right? There's no extra electrons, nothing else is going on there. So every time you see this AX2, you know it's going to be triatomic linear because they're connected. That's how it works, all right? All right, let's draw this out. Draw this structure of the central atom. So it's Be, all right? And how many valence electrons does beryllium have? It has 2. How do you know they have to be across from each other and not next to each other? Goes back to this, AX2, right? They're across from each other, so you're going to draw them across. Now you could draw them up and down, that's fine, but they have to be across from each other because everything that's AX2 will have this kind of shape. Okay, and then we have hydrogens we're going to add, and we'll add them here and here for the same reason as we did for H2, because if they have 1 electron, they're going to want to share with another electron. Because now the hydrogen's happy, it has 2 around it. And then this hydrogen's also happy, it has 2 around it. Now this is an exception because usually everything besides hydrogen wants to have 8 around it, but this only has how many around it, the beryllium? It only has 4, yeah. 2 from over here and 2 from over here. So beryllium and those group 2, if they do this, if they covalently bond, they're gonna form like this. Okay, not all of them are covalent, but we'll talk about that more later on. All right, so how many non-bonding electron pairs are on the central atom? 0, right? There's no extra electrons there. What about single bonds? How many do we have? 2. And let's talk geometry. What's the angle? 180. Yeah, exactly. 180 degrees, right? Makes sense. It's a line. Okay. Let's look at the next one. Let's talk about its AX pattern here. Does it have an A? Yeah. Does it have an X? Yeah, how many? 3. So every time you have 1 A and 3 X's, it's going to have this shape. So we're going to call this AX3. All right. And there's 3 external atoms here, right? There's 1, 2, 3, and then there's 1 in the center. So we're going to call this trigonal. And then look at it. What is its geometric shape? If you look at it like this, you can see all the atoms. But if you look at it this way, what do you notice about it? They're all on the same plane. Yeah, so it's trigonal planar. All right, trigonal planar. All right, let's look at the central atom here. The central atom's going to be, what was this one? Boron? Boron H3. So I'm going to put a little B here. How many valence electrons does boron have? It has 3, right? How am I going to draw them? Yeah, kind of like a triangle, right? Because we're going to have one maybe up here, maybe down here, down there, because we want to have that shape, right? We want to have that trigonal planar shape. And then the hydrogens will be attracted to where those electrons are, and they'll share them. All right, so then we'll do a connection here. And then it looks like this. It's just turned a little, which is fine. You can do that. All right. How many non-bonding electron pairs does this one have? 0 as well. And then how many single bonds? 3. Angle. Yeah, 120, right? Awesome. Okay, everybody's cool with that? Yeah? Let's look at the next one. Does this have an A? Yep, how many X's? Good. So this one we're gonna call AX4. All right, and the name, there's 4 external here. We use the same kind of thing from nomenclature, so we're gonna use the word tetra in here. So it'll be tetrahedral. All right, tetrahedral. All right, tetra for 4. And then we need to draw it. How many valence electrons does this have? It's 4, right? Carbon. It's 4. That's where we built CH4. All right. So carbon has 4. Where are they going to go? Now this is a little bit more difficult because we're drawing this on paper, which is 2-dimensional. This is the shape we want. This is kind of how we're going to represent it on paper. All right. It's not the best. You can see it looks different when you have it built. It's not flat like that one. It's more like this, right? But you could kind of turn this in such a way that you could see, all right, 1, 2, 3, 4, it kind of has that shape to it when you're looking right at it. It's okay. All right, we'll put the hydrogens around it. And this is the first non-exception. How many electrons are around this carbon now? 8, and that's what it wants, right? How many were around this boron? Yeah, there were only 6, right? This one has 8, so this is great, okay? How many non-bonding electron pairs? Still 0, yeah, there's no extra electrons. And then how many single bonds? 4, okay. What's the angle? 90. Okay, so no, it's not 90 because it's not flat, right? This looks 90, but remember I just said it really looks like this. If you were to hold this up and look at it, you can see that's more than 90 degrees, right? So, yeah, so I mean, we'd have to guess, right? Or have a tiny protractor. So 109.5. Okay, so let's go over this. What's the AXE pattern for this one? Does it have an A? That's when you say yes. All right, good. And then what about X's? How many X's does it have? 3, good. Okay, so we have these 3. And then what's the thing at the top here that looks like a ghost? What is that representing? We don't know? All right, let's draw it out and let's see if we can figure it out. Let's go over to here. How many valence electrons does nitrogen have? It has 5, right? So 1, 2, 3, 4, 5. All right, what's the ghost thing?
Unpaired electrons.
Yeah, we have some unpaired electrons, right? So that just represents 2 electrons in there, okay? So we have A, X, 3, and then what's up here? The electrons. So this is the first time we would use AX3 and then E. And a capital E represents a pair of electrons. So you only need 1 E, and that covers both of the electrons, okay? Now, if we look at this one, what was the difference between this AX3E and this regular AX3? Do you remember what shape this one was? Well, it says the name right there. What did that planar mean? Yeah, it was flat, right? Is this one flat? No, when you build this one, it's not flat. It kind of like stands up if you were to hold it, right? And if you gave it sides, what would it kind of look like?
A pyramid.
Yeah, exactly. It kind of has a pyramid shape, and this one was a flat shape, all right? The difference between those two are the electrons, and the electrons being on the top force the other atoms to go down, and that gives this shape what it is. So in this one would be trigonal, pyramidal. All right, so that's our shape for this one, trigonal, pyramidal. All right, and we have 3 X's, right? And we know we have 3 hydrogens. So just like before, the single dots, they get those hydrogens. So we'll get a hydrogen, 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 and then they'll bond together. So we'll get something that looks like this. All right. Now, how many non-bonding electron pairs do we have on the central atom for this one? Yeah, now we actually have 1 pair, right? There's 2 electrons, but there's 1 pair. And then how many single bonds? Good, 3. Now look at it. What's the angle for it? Get out a tiny protractor. What does it look like? Is it 90? It's more than 90, right? When you look at it, it's a bit obtuse. Good, all right. 107. All right, 107. All right. Okay, everybody's cool with that one? Yes? All right, last one we have here is water. So, does it have an A? Yes. Does it have an X? Yeah, how many? 2, good. And then does it have E's? Yeah, how many? 2. So this is AX2E2, right? It has 2 of these electrons up here. As opposed to this one up here, which was just AX2, this one was linear, right? It just straight across linear. What's this one now? If you were to compare the 2 shapes, linear versus, okay, that's okay. Non-linear, not straight, but what is it? It's bent. It's bent, all right? If you want to sound fancy, you could call it angular. But bent is fine for this one. It is bent. All right, how many valence electrons does oxygen have? It has 6, good. So let's draw them out. We'll have 1, 2, 3, 4, 5, and then 6. And the trick with this one is the 2 paired electrons are always going to be next to each other. They're never going to be across from each other. All right. You can see it right here. They're next to each other. That's what causes the bend. All right. They're not going to be across or across. You can rotate this any way you'd like. You could have the double bonds on the other side. They just have to be next to each other. All right. And so there's 2 single dots here, 2 single electrons. So we can have a hydrogen bonded here, and then a hydrogen bonded here. Okay, how many non-bonding electron pairs do we have? Good, we have 2. All right, and then how many single bonds? We have 2. What's the angle?
100.
Again, it's somewhere over 90, right? It's somewhere over 90, even though this drawing looks like it's 90, right? And it's not a great drawing, but okay, it's 2-dimensional. I guess we could draw it a little bit better. It's 104.5. So this one was 109.5, right? This is 107, this is 104.5. Why are they all different? The difference here is you're replacing atoms with electrons, and that has this kind of push to reduce the angle slightly, and that's why those basically decrease as you go down there, okay? Okay, any questions with any of that, the chart?